Hello, here's going to be a lecture about an introduction to multiple linear regression in R. Before we get to that, let me show you just a little trick that I use to make it easy for me to move to the right working directory quickly when I open up RStudio. So I have a file that I always keep loaded called it's called working dirs 2. And then I keep some common directories that I work on. So here's the one for our course, and I can just run this line by doing Control Enter on my computer. There should be I'm in Linux, specifically Ubuntu here, but there should be an analogous command. I think on Macs it's like Command Enter. All right, so now I'm in the right working directory, and in that directory I have a file called multiplelinearregression.r, and this is going to be our introduction to multiple linear regression for this course. Since this is statistics, we're working with data sets, and so I want to do a little short digression into how R loads data sets from R packages. So R is this computer program, but it's also kind of an ecosystem for people to develop their own software. And along with that software, people often include data sets where people can try out their software in those data sets. So all this stuff gets put into a package by the author, so this is called an R package, and it's uploaded to a central repository called CRAN, and they do all sorts of checks to make sure the software works, and then it's available to you, the R user, easily in R. All right, so I want to look just briefly on how R loads packages, loads data sets with packages. One of the data sets we're going to be working with today is the Berkeley Guidance Study data set, which is called BGS Girls, and this is part of the ALR4 package, which is the R package that's associated with the one of the textbooks that we're using for this course, Applied Linear Regression. All right, so if I were to just start an R session like this, and I were to try to run this line, the data set's going to be called BGS Girls, for Berkeley Guidance Study Girls. I get an error here because I haven't loaded this in at all. Now, for reasons that will become clear in a minute, I'm going to just define this object, BGS Girls, as 7. All right, so all I'm doing there. And now I'm going to load in the package. So I've loaded the ALR4 package. The command for seeing what objects are loaded into your R workspace is called ls, so it's a function. And you can see that it sees this BGS Girls object, but the question is, what is that? Is that the object we defined here, or is that the one that gets loaded in with the package? And if you run this, it prints out 7. So when R loads this ALR4 library, it won't override any objects that you've already defined. So for example, if I want to explicitly load in this data set, I can call the data function with the argument the string BGS Girls. And this will look through all of the R packages that are loaded, and if there's a data object called BGS Girls, it will load it. So now if I do some operation on this BGS Girls object, like head, now this is the actual data set that we want to work with. And this has overridden this assignment of the number 7 to the object BGS Girls. Okay. So that's one way to do it. You load in the ALR4 library, and then you call the data function to load in that specific data set. All right, so what I want you to do now is to click Session up in the menu up here, and then restart R to start a new session. So what you should see in your panel on the right here is that it's restarted a new R session. And now if I do ls, there's nothing in there. By the way, my setup of RStudio may be different from yours. What I've done is I've gone into the options and I make sure that the left panel has the R scripts and then the top right panel has the R console. So I can minimize this, and its left side is all R scripts and the right side is all panel. I think this is a good way of organizing your workspace. It's not the default, so people are going to disagree over whether this is a good way to do it. But it kind of, I think it's good practice to center the script, to make that sort of the thing of interest in your workspace, because that really is the thing of interest. All right. So we just restarted a new R session. Let's load the ALR4 package with the library function. Okay, you see it does a bunch of stuff. By the way, in RStudio, you can switch between the R script and the console by doing Control-2 to switch to the console and Control-1 to switch to the R script. It's good to learn these keyboard shortcuts. It kind of makes your life a lot easier. One other thing, I'm using the Vim key bindings. So my cursor is going to look a little bit different from yours probably. In some other video, I can show you kind of the power of this, but we'll skip over that for now. Okay, so I've loaded the ALR4 package. If I do ls again, it sees nothing. Okay, so that's kind of interesting. It says there's no actual objects that get loaded. However, here's something that's a little weird. If I do head of BGS girls, it sees the BGS girls object. Okay, this is something that I learned relatively recently about R packages and the data sets. That the data sets aren't explicitly loaded into the R workspace. It's something called lazy loading, which is kind of a technical concept. But they're there. Even though they're not printed out when you do ls, you still have access to them. So even though I can, I do ls, I get nothing. I do this, I see the data set. I do ls again, I get nothing. I can access one of the columns of BGS girls. So if I take the first column, that's WT2, and that's there. Even though there's nothing, ls shows nothing in the workspace. All right, so that's another way of doing it. Just call the library function on the package that contains the data set, and it automatically does this lazy loading of the data set. Now I want to show you the way I prefer to do it. So what I want you to do is to click again session restart R to start a new session. And I want to show you what I think is kind of the preferred way to do it. So one thing you want to try to avoid programming in general is to avoid loading in things into your workspace that you're not actually going to use. The reason for that is you may load things that you don't know that you're loading. So for example, when I do this library ALR4 up here, it not only loads the BGS girls dataset, it loads a whole bunch of other datasets. And some of those dataset names, you might try to inadvertently call the object with those dataset names without having ever defined anything, and your code will run even though that's not really what you want it to do, and this will be what's called like a silent bug, which can cause all kinds of problems. So the general principle is you want to load the minimal number of objects that you really need for your analysis. So one thing you might try is just to say, I'm going to do data BGS girls. This does not work. The reason is because the data function just looks at the packages that are already loaded and then looks for a data set called BGS girls in those packages. So if I try to just print it out, BGS girls, I get an error here. It's not found. So when you use the data function on a package that's not already loaded, you have to specify the package name. So there's an additional argument in the data function called package, and this will load in the data set. So if I do ls, now it sees an object. So I like this better because it's only, so if there's another data set in BGS girls called water, and that does not get loaded. So this just loads the one data set that we're going to use. And I also like this, that it explicitly loads it into the workspace so that it's visible when you do the ls. So there's no sort of ambiguity here about what's loaded and what's not. It's all very explicit. So this is the way I prefer to do it. I can look at the head of the data set. One potential issue with this method is because I haven't loaded the ALR4 package, the entire package. It actually doesn't load the documentation for this data set. So every data set in an R package will have a documentation file associated with it. So if I do Control Enter on this, I get this message, no documentation found for BGS girls. The way to access any function or documentation for a function for a package that's not loaded is with this syntax here. You put the package name, ALR4, double colon, and then the object that you want to get documentation for. So if I do this, then I will get the documentation. So this is a file that's worth reading that tells you things that you need to know about the data set. So it tells you where it comes from. It tells you what kind of format it's in. It's a data frame, has these columns. Here's the units and all the variables for that data set. Okay, so this is worth looking at. In the analysis to follow, we're going to be using height at age 18 as the response, and then we're going to look at various different columns as predictors of height at age 18. So that's the end of our little digression about data sets in R packages. If that was all a little confusing, that's because it really is confusing. I just learned about this recently. So if your conclusion from all of this is, I don't understand how R loads data sets with packages, that's good enough for now. My main goal is, if not to just to show you how this works, but to convince you that it's not obvious how this works, that's fine, because then you'll be a little bit more careful when doing this. When in doubt, kind of use this flow, this one in particular, because this will explicitly load this data set from this package. Okay, so let's move on to multiple linear regression. We're going to use this BGS girls data set, so I'm not going to restart the R session. I'm just going to go ahead. And the first thing I want to do is I want to plot the response, which is height at age 18, against some of the variables that are available at ages 2 and 9. So this is a longitudinal study of children, and they made a bunch of biometric measurements like heights and weights and things like leg circumference over time. And they measured them at age 2 and age 9 and at age 18. Okay, so what I want to do is I want to plot the response against three of the variables. The three variables we're going to look at are height at age 2, height at age 9, and leg circumference at age 9. So what I'm going to do is I'm going to set up a panel of plots with 1 row and 3 columns. Now the function, which is very powerful for manipulating graphical parameters, is called par. The documentation for par is worth reading on its own, just kind of like start to finish. It's pretty long, but you'll see all the sort of things that you can modify in the plots. One of the common ones that gets used is called mfrow, and there's another one called mfcol. So what this says, mfrow, I give this a vector of length 2. The first element, So what this is going to do is it's going to set up a grid of plots. And this mfrow argument tells us what is the dimension of the grid of plots. And the first is the number of rows of plots, and the second element is the number of columns. So this sets up a panel of plots with 1 row and 3 columns. And then every time you call the plot, it fills in the next plot from left to middle to right. So if I do, let's see, did I run this? I have to run this. And then if I do this, it's going to fill in the first plot in this panel. This fills in the second one, and this fills in the third one. What I'm plotting here is on the horizontal axis, one of the variables. On the vertical axis is the response, and then I put some labels on the axis. Okay, so let's take a look at the plot. So it's a bit hard to see with this aspect ratio, so let me make it smaller. All right, so the first one's height at age 2, and second one's 9, and then the third one is leg circumference, age 9. If you were going to pick one predictor variable for height at age 18, you would probably pick height at age 9. You would probably pick that out of those 3 without even looking at the data. It's just kind of natural that that would be the best predictor of height at age 18. And if you look at the data, that is kind of borne out in practice here. So height at age 2 looks like it's positively related, but not as strong as height at age 9. Leg circumference is less so, but it looks like maybe there is a slight positive relationship. This one may or may not be significant. One kind of rule of thumb for trying to figure out if a regression is going to be significant is if you can take 1 or 2 points and move them and change the conclusion, then it might not be significant. So for example, if I took this top right point here and I moved it down here, then it might look like there's a negative relationship, whereas if you look at this, it kind of looks like there's a positive relationship. So I wouldn't be surprised if we did the regression here and found that there's no significant relationship between these 2 variables. Okay, so let's go through one by one, and we're going to do the regressions individually. Actually, we're going to start with just height age 2 and height age 9. So let's reset this to be a 1-by-1 plot, because I'm just going to do one at a time. So this will plot height at age 18 versus height at age 2. We're actually not going to use that, so that's just to make the plot bigger. So I'm going to make this smaller. And if we go back to this side, the function for doing regressions in R is called LM. And the syntax works like this. I put the response first, and then I do a tilde, and then I put any predictor variables after the tilde. Now this entire expression here is called a model formula, and that expression, that model formula, is the first argument to LM. So we'll be adding more terms in the model formula, but you can think of this thing that's highlighted as a single kind of R object, and it's an expression, and it itself is an argument to the LM function. Now there are other arguments to the LM function. One of them that we'll be using is called data. This tells us which data set to look in to find these 2 variables. So if you go over to the console and you were just to type HT18, you get an error. There's no object in your workspace called HT18. There is an object called BGSGirls $HT18. But if you were just to try to run LM without this data argument, it would look for an object called HT18. It would not find it, and it would give you an error. So this LM function is convenient because it allows you to write down the model formula without typing out this whole thing, BGSGirls $HT18 and BGSGirls $HT2. But then you have to specify which data set to look in to find those variables. So this fits the model. And then the summary function will spit out some information about the model fit. So the thing we'll be looking most closely at is this table of coefficients here. So this says the intercept, which is the B0 in our model, is 60.97. Height at age 2, this tells us the B1 coefficient, the coefficient multiplying height at age 2, and that's 1.2099. All right, so how do we interpret these things? The intercept is the expected response when the covariate is equal to 0. So you expect height at age 18 to be 60 centimeters when height at age 2 is 0. Now this is clearly outside the range of our measurements. We're not going to have anyone in our data set whose height at age 2 is 0. So this thing is not particularly interpretable. It's kind of something we're trying to intercept is like an extrapolation away from the data. The thing that's more interpretable is this thing. So what this says is for every increase of 1 centimeter in height at age 2, we expect an increase of 1.2 centimeters in height at age 18. Now, first thing to realize is that that's a number larger than 1. So it's like differences in heights at age 2 get kind of amplified as you when you look at heights at age 18, which kind of makes sense. Sort of the range of variation of heights at age 2 will be smaller just because the overall heights are smaller, whereas the range of variations at heights at age 18 is larger. So this kind of makes sense. The other parameter that we estimate in a linear regression is the sigma squared. So R will plot the estimate of sigma, and it calls this the residual standard error. So this thing here is sigma hat. R also tells you the degrees of freedom. And remember, usually when people say degrees of freedom without any modifier, they mean residual degrees of freedom. So this is 68 residual degrees of freedom. Now that tells you that there were 70 observations in the data set because the model degrees of freedom is 2 and the residual degrees of freedom plus the model degrees of freedom is the number of observations. And then it also prints out some additional stuff, R squared, which we talked about, and an F statistic, which we'll get to in a later lecture. Okay, so that is the height at age 2 simple linear regression. We can do the same thing for height at age 9, just to remind you of what the data set looks like. It's this. And then M2, I'm going to call this the fit of height at age 2 against height at age 9. So it's very similar to M1, except I'm replacing the 2 with a 9 here. And here's the summary. Now we get a different intercept, which again is not going to be interpretable because that would correspond to an expected height at age 18 when height at age 9 is 0. And then we get height at age 9, the coefficient is 0.87. So this says that for every increase of 1 centimeter in height at age 9, we expect an increase of 0.87 centimeters in height at age 18. And by the way, this thing is statistically significant. What this number means, it's very small, very close to 0, is that we have very strong evidence that this coefficient is not 0. We also have very strong evidence. This p-value is 3.92 times 10 to the minus 10, which is also very small. We have very good evidence that this coefficient is not 0 as well. Okay, so we think that height at age 2 and height at age 9 are both linearly related to height at age 18. One question you might have is, if we're going to pick one of these two, which one is the better predictor? Well, you can probably guess how this is going to turn out based on your intuition and based on looking at those scatter plots. But one way of sort of formally doing this is to look at the residual standard error. So if I want to pull out the estimate of sigma from the model, I use a summary of the model object $sigma. So that was about 4.58 from the age 2 model and 3.6 from the age 9 model. So this says that the age 9 model has a smaller residual standard deviation or residual standard error. Therefore, your predictions of height at age 18 are going to be better with the age 9 model, which makes a lot of sense. The other thing to look at is R squared. So R squared is 0.65 for the age 9 model versus 0.44 for the age 2 model. So that's additional evidence that age 9 is a better predictor. So that's one at a time, but what if we include both of these variables in the model? So that's what we're going to do next. So the syntax in R for doing the multiple linear regression of height at age 18 on these two variables is very similar. So to do multiple variables, you just list them out in the model formula, and then you put a plus between them. So this fits the multiple linear regression with height at age 2 and height at age 9 in the model. Now, before we fit this model, what I want you to do is to pause the video and think about what you expect the results to be. And keep in mind that the interpretation of the coefficient is the effect of the variable after controlling for the other. So the coefficient that we're going to get on height at age 9 is our best guess of the effect of height at age 9 our best guess of height at age 9 while controlling for height at age 2. And then likewise, the coefficient that we get on this one is our best guess of the effect of height at age 2 while holding height at age 9 constant. So go ahead and pause the video and think about that for a minute. Okay, we're back. So let's just do it. So here's the model fit, and here's the summary. So here's what we get. So again, the interpretation of the intercept is not all that meaningful. This is our expected height at age 18 when both of these variables are 0, which never happens. So this variable, what this means is that we expect height at age 18 to increase by 0.27 when height at age 2 is increased by 1, but height at age 9 is held constant. And then likewise, this is the effect of increasing height at age 9 by 1 while holding height at age 2 constant. Now, if you look ahead at the standard errors and the t-statistics, what we find is that the height at age 9 coefficient is highly significant. So this is a number that's very close to 0. So the way we interpret this is that we have very strong evidence that height at age 9 has a linear relationship with the response after controlling for height at age 2. Now, if you look at the height at age 2 coefficient, its p-value, this is not considered statistically significant. So this is a t-statistic that would not be unusual under the hypothesis that the effect of height at age 2 is 0 after controlling for height at age 9. Okay, so maybe this is surprising to you. Maybe this is what you expected to happen. But really what this is saying is that the height at age 2 provides no or very little information about the height at age 18 after you know the height at age 9. So it's not estimated to be exactly 0. Our best guess of this effect is that it has a positive impact on height at age 18 after controlling for height at age 9, but we can't with any confidence say that this effect is not 0. Okay, so based on statistical significance, looks like this is the more important variable, But statistical significance, remember, that's just a measure of our strength of evidence and not necessarily a measure of the strength of the relationship. So in multiple linear regression, it's harder to come up with a sort of a ranking of the effect of each of the variables, but there are some kind of crude things you can do. One thing you can look at is you can compare the residual standard error of the model with both variables. You can compare that to the residual standard errors for the model with each of the individual ones. So if you recall for here, so this is the model with just 9, you got 3.6, whereas you get 3.58 here. So it actually doesn't go down much if you add height at age 2 to the model with height at age 9. If you look at height at age 2, we got 0.44. So if we add height at age 9 to the model, it goes from 0.44 down to, that's the R squared. It goes from 4.5 down to 3.6, which is or 3.58, which is a more significant decrease. Another kind of crude measure is you look at the variation in the variable, so it's standard deviation, and multiply that by the coefficient. So the reason for this is, if you look at the coefficient for height at age 2, when it was alone in the model, it was about 1.21, which was actually larger than the coefficient for height at age 9. So it would be a mistake to conclude that since this coefficient is bigger than this one, then this is a better predictor of the response. That's a mistake because that doesn't agree with our better measure, which is the residual standard error or the R squared, which both say that this is the better model. So just the raw size of the coefficient is not actually a good measure. You should at the very least compare it to the actual amount of variation in the variable. So that's what we're doing with this piece of code here. So basically the units of this coefficient is it's like change in the response per change in the covariate. So if you want to see sort of a better measure of how much this variable affects the response, you can multiply it by the sort of the average variation in the covariate. So the units of this quantity is actually change in response. So this is the effect of height at age 2 on the response. So a 1 standard deviation change in height at age 2 on the response. And this is the effect of a 1 standard deviation change in height at age 9 on the response. So it's more than 4 times larger. So that's additional evidence that the height at age 9 is a better predictor. Okay. All right, so let's dig a little bit deeper into why this coefficient, height at age 2, is significant, whereas this coefficient, height at age, this one's not significant, whereas this one is significant. So one way of thinking about this is, since the interpretation of the height age 2 coefficient is the effect of height at age 2 after controlling for height at age 9, we can sort of look at the relationship directly by looking at the residuals. Okay, so the conclusion from the model fit is that height at age 2 does not explain the variation in height at age 18. That's not explained by height at age 9. If you think about it, the variation in the response that's not explained by height at age 9 are the residuals from the model that just included height at age 9, which is model number 2, M2. So we can actually do a scatter plot of height at age 2 and the residuals. So we're going to plot the residuals from the model that just contained height at age 9. And we're going to plot that against the height at age 2 variable. So the way we think about this is that the vertical axis is the variation in the response that's not explained by age 9 height. And then we're seeing whether we can explain that with age 2 height. And if you stare at this plot, it's going to be hard to convince yourself that there's a lot of information in the age 2 height that's relevant to the age 18 height, or the variation in age 18 height that's not explained by height at age 9. Now we can do the opposite one. So what we concluded from the model fit is that height at age 9 does explain some of the variation that's not explained by height at age 2. And this variation that's not explained by height at age 2 are the residuals from the model that included age 2 only. So we can make the equivalent plot here. Now, what we're looking at in this plot is the vertical axis is the variation in the response that is not explained by height at age 2, specifically a linear relationship with height at age 2. And then we're trying to see if we can explain that variation with height at age 9. And here it does look like there's some kind of positive relationship. So after we control for height at age 2, there's still some additional information about height at age 18 included in height at age 9. Okay, and then another way of probing this is we're just going to do a straight up regression of those residuals on height at age 9, and we get a highly significant relationship there. Okay, now the other variable we want to look at is leg circumference. And this might turn out a little bit surprising to you, but I think it's not if you think about it carefully. So let's first do what we did before. We're just going to do a regression of simple linear regression of age 18 height on leg circumference at age 9. And we see a positive relationship. It's, I guess, significant, statistically significant by some pretty stringent measure, so it's less than 0.005. So it looks like we do have evidence that there's a relationship between height at age 18 and leg circumference at age 9, and the relationship is positive. So the bigger your leg circumference at age 9, the taller we expect you to be at age 18. So what I'm going to do next is I'm going to throw out, forget about height at age 2 because it doesn't seem like that helped beyond height at age 9. And I'm going to put in, instead of height at age 2, I'm going to put in leg circumference at age 9. So let's do that. And then I'm going to do a summary of the model. And here's what I get. Now the height at age 9 coefficient is positive. It actually gets a little bit bigger than it was before. It's 1.02. But the leg circumference, remember that was positive in the simple linear regression on leg circumference. This becomes negative in this model. So the way we interpret this is that for every increase of 1 centimeter in leg circumference, while holding height at age 9 constant, we expect a decrease in height at age 18, and the decrease is minus 0.58 centimeters. And on top of that, it's not just probably not just a spurious result. This is statistically significant, which means we actually have pretty good evidence that this coefficient is not 0, and it's negative. Okay, so this might seem a little bit weird at first. Just to summarize this is our model with height at age, this should be a 2. This is our model with age 9 height only, and we're looking at the estimated sigma. We get 3.6. When we add age 2 to that, it goes down to 3.58. If we instead add age 9 leg circumference, it goes down to 3.44. So if I have age 9 height in the model, I actually prefer to add leg circumference age 9 to the model rather than height at age 2 to the model. Okay, so something to think about. We could discuss this in the office hour. It did turn out that the coefficient, it wasn't significant, but the coefficient for height at age 2 turned out to be positive when we included it in the model with height at age 9. So can you think of a biological reason why the age 2 coefficient is positive in the multiple linear model? And can you think of a biological or logical reason why the leg circumference age 9 coefficient is negative? I think this makes sense if you think about the biology. Keep in mind, though, that your answer must grapple with the fact that the interpretation of the coefficient is the effect of the variable after controlling for the other variable, which is the height at age 9 variable. Okay, so we can discuss that in the office hour. If you look below, there's additional code for doing regressions with temperature data. I'm not going to go over that in the video, but you can feel free to look at that. There's some quirks about plotting ticks that maybe you should look at carefully if you want to use base R graphics. So you can look at that yourself, and we can also talk about it in the office hour if you have questions about it.